Hello everyone, we will start a new module today and that will be on source coding. So, we will cover these topics under source coding. Out of these topics, we will cover the following 3 topics in this class. First, we will have introduction. So, there we will see why we need source coding and why it is possible to do source coding for most of the sources. And then we will describe some of the desirable properties of source codes, and in particular we will discuss what is called uniquely decodable codes and prefix codes. And then we will discuss one particular very popular source coding technique called Huffman Code. This source coding technique is a very important source coding technique and we will see why later, and rest of the topics will be covered in later classes. So, let us see why we need source coding. So, this is a typical communication system. It involves one source which generates the message or information that is to be transmitted through a channel to the destination. It generates a continuous time signal or a discrete time signal, and the destination receives a distorted version of the signal yt or yn, and the channel distorts the signal in some way or the other. And so, why do we need source coding? Because the signal source generates may have redundancy or undesired or unimportant extra information that the destination does not require. For example, telephone quality speech can be compressed without compromising much on quality to as little as 1 to 2 kbps data rate. So, even if we do not consider all the nonsense we talk, there is a lot of redundancy in the representation of the signal itself. So, here is a particular example where you will hear a particular original audio recording and then a compressed signal which will be compressed to 1.5 kbps. So, here is the original signal.
Only lawyers love millionaires.
So, we hear the same signal compressed to 1.5 kbps now.
Only lawyers love millionaires.
As you can see, there is not much difference, at least there is no perceptible difference between the two signals. So, that means all the information that the original recording content is more or less contained in the compressed version as well. So, here is a particular example of how one can do source coding. This is a very typical example. The example is of sampling. So, if we have a band limited continuous time signal of bandwidth W, and if we sample that signal at sampling rate greater than or equal to 2 times W, that is the Nyquist rate, then we know that we can recover the continuous time signal back from the sample signal. So, that means that there is no loss of information when we sampled this continuous time signal at a rate greater than or equal to 2 times W. And that in turn means that all the intermediate values between the samples which we have discarded did not really contain any extra information over what these samples contain. So, intermediate values were really redundant. Another reason why we may need to do source coding is that the channel through which we are going to transmit the data may not have the capacity to communicate at the same rate at which the source is generating the information. So, in such a situation, we may need to compress the source with some loss of information. So, we have already seen 2 types of source coding. One is one in which there was no loss of information, and here is another where there is some loss of information. And here is an example of source coding with some loss of information. If we have a real valued sample signal, every sample contains infinite information, because the precision of the sample is infinite. So, to transmit this these samples through any finite capacity channel, we need to quantize the samples before transmission. So, that quantization will involve some loss of information. Another reason why the source, another way the source signal may contain redundancy is through non-uniform distribution of the source. The symbols source generates may have non-uniform distribution, and as a result the representation of the source may be improved. For example, in a typical English text, we know that some letters come very frequently and some letters do not come so frequently. So, when you try to represent the English text, every English letter using binary sequences, it will be a good idea to represent the frequent letters using smaller number of bits and rare letters using longer bit sequences. And this is exactly what is done in Morse code, which is a very traditional code used for telegraphic communication. You might have seen in movies or even in labs a small instrument through which telegraphic information is transmitted by pressing a key in different ways. So, a very short small sound of dot and combination of dots and longer sounds of dashes actually communicate the letters. So, every letter in Morse code is represented by a sequence of dots and dashes. So, in Morse code, the most frequent English letter E is represented wisely by a single dot, and not so frequent, in fact very rare letter Z is represented by a longer sequence of dots and dashes, that is 2 dashes and 2 dots. So, this is a very traditional example of this type of source coding, where the source coding is possible because of the non-uniform distribution of the symbols generated by the source. So, we have seen two types of source coding. One is lossless, where there is no loss of information due to coding, and this is used by various file compression techniques in computers. For example, compress in Linux or WinZip in Windows. And then another type of source coding called lossy source coding, which involves loss of information. And we have seen, in fact, that quantization is an example of such source coding, and vector quantization is a generalization of source coding. We will not discuss this technique in detail here, and subband coding is another very popular source coding technique. And all these techniques are used, these lossy source coding techniques are used in standards like JPEG, MPEG, etc. From now on, we will consider lossless source coding for discrete memoryless sources. So, we will see what discrete memoryless source means. A discrete memoryless source generates these symbols in discrete time, x 0, x 1, x 2, each of them is a random variable, and each of them takes values from this set. So, m possible values, and each of them has some probability, and we assume from now on that these probabilities are known to us. While designing source code for this source, these probabilities will be assumed to be known. A typical example of discrete memoryless source is an analog source sampled and quantized. Sampled to make it discrete time, so it is discrete, and quantized to make this set finite, because each random variable should take finite number of values. And it is memoryless means that each symbol here are uncorrelated from each other. So, to make a sample signal memoryless, we actually need to sample the analog signal at a lower rate. So, if we sample an analog signal at exactly the Nyquist rate, we will get a memoryless source. If we sample at a higher rate, we will not get a memoryless source, memoryless sampled output. So, let us see, without doing source coding, what is an obvious way of coding the discrete memoryless source. So, every symbol takes m possible values, and let us say that m is less than or equal to 2 to the power b. In fact, we will assume that m is greater than 2 to the power b minus 1, but less than or equal to 2 to the power b. That is, to represent this symbol using binary streams with equal length binary streams, we will need b at least b bits. So, we have all these symbols as possible outcomes of the source, and each symbol needs to be represented by a fixed length code. So, if we code using fixed length code, we will need b number of bits for each of these symbols. Even though they have different probabilities, we are coding them with equal number of bits. This will require b number of bits per symbol, whereas we can do better. If we have, for example, 4 symbols with these probabilities, these unequal probabilities, if we want to do fixed length coding, we will need 2 bits per symbol, because there are 4 symbols here. So, average number of bits required per symbol is 2 bits using fixed length code, whereas if we use a variable length code like this, then what is the expected length of the code? It will be 1 times 0.5 plus 2 times 0.25 plus 3 times 0.125 plus 3 times 0.125, and that will give us 1.75 bits per symbol. So, here we have been able to represent the source with less number of bits on average than using a fixed length code. And in fact, this is the best for this random variable we can do, because entropy of the source itself is 1.75, and by the source coding theorem of Shannon, this is the minimum number of bits required to code the random variable. Okay. So, here are some desired properties of source codes. Obviously, 2 different symbols should not be coded into a same code, because if done that way, if we receive a code word, we will not be able to decipher we will not be able to decode the code properly at the destination, because if we receive that code word, we will not know which one of these 2 were transmitted, because code for both these symbols are same. So, this code cannot be decoded uniquely at the destination. For example, so this is that kind of code will be called singular, and the code where every distinct symbol is encoded into different code sequences is called non-singular code. So, for example, this code is a non-singular code, because all these 4 code words are different. But even if we have these even if we have a non-singular code, we may not be able to decode a code uniquely. We will see later an example of that. So, for now, we will note that singular codes are not useful. That means, we should have distinct code words for each different symbol. So, just now we said that even if we have a non-singular code, it may not be uniquely decodable. So, what can go wrong? What can go wrong is this, that if we now we will be transmitting these symbols one after another. So, if we transmit m consecutive symbols, so and the total code sequence for that will be this. If we receive this code sequence, it should not be code sequence for any other symbol sequence. That means, if we have 2 distinct symbol sequences, their code sequence should not be, their code sequences should not be same, so that the decoder can decode this whole string uniquely. Okay. So, are there non-singular codes which are not uniquely decodable? Yes, in fact, there are. We have in fact seen an example in the last slide. We will see again this code 0, 0, 1, 0, 0, 1 and 1, 0. This code is obviously non-singular because all the code words are different, but if we receive this string can be decoded in many different ways. If we break this string into 0, 1 and then 0, 1, 0, then we will think that we have received this symbol and then this symbol, but if we break this as 0, 1, 0 and then 1, 0, then we will think that we have received this one first and then we have received this one. On the other hand, we can also break this string into 0, 1, 0 and 1, 0. So, we will think that we have received this, this and this symbol. So, a non-singular code need not be uniquely decodable. So, this is a non-example, this is not an example of uniquely decodable code, whereas this here is an uniquely decodable code. We will not check that this is uniquely decodable, there are ways of checking that, but we will not go into that now. Okay. So, even for uniquely decodable codes, we will not be able to decode the received sequence instantaneously, meaning by whenever we have received a code word, we may not be able to decode that code word instantaneously. We may need to wait for some longer time to see what are the future bits we receive, and then we will be able to decode the whole sequence. So, we need to wait for future symbols before we can decode a present symbol. That is the problem with uniquely decodable codes in general. So, we need to be able to decode instantaneously, we need some more properties, and that is here. We need prefix codes, meaning by any code should not be, any code word should not be a prefix of another code word. If that condition is satisfied, the code can be decoded instantaneously. So, here is a non-example. We have seen this example before. This is a uniquely decodable code, but this is not a prefix free code. Prefix codes are also called prefix free codes, and this is not a prefix free code because this code word 1, 1 is appearing as a prefix of this code word. So, if we receive this stream for example, then this stream is 1, 1, 0 one code word, then 0, 0 another code word and then 1, 0 another code word. So, 3 code words. But after we have received 1, 1, 0, we will not be able to decode this immediately, because after receiving 1, 1, 0, we may think that this may be 1, 1 and then 0 is the starting of another code word, this one. So, we do not know whether it is 1, 1 or 1, 1 and 0, 0 or 1, 1, 0 and future bits. So, we have to wait longer to decide on that. So, in fact, we will have to wait till all these 6 bits before we can decode the first symbol for this code. So, we see that this code cannot be decoded instantaneously. So, here is a prefix code, and for prefix codes we can decode instantaneously, because whenever we have received a code word we can decode that. Every time we check, we receive first 1, then we receive 0, then we know that that is a code word. So, we can decode that, because this cannot be part of this cannot be prefix of another code word. So, this is surely the code word we have received, and all the future bits can be decoded fresh later. So, the prefix codes are the best among these 3 classes. All these are desired properties, but prefix code is uniquely decodable. So, it is also non-singular. So, here is a summary of all the classes of codes we have considered. Singular, obviously this is the most trivial example of a singular code, all the code words are same. non-singular but not uniquely decodable. We have seen this particular example before. This is non-singular, but this is not uniquely decodable because we can combine a few code words and then we will get a string which can be decoded as string of two different strings of symbols. And this is uniquely decodable, but not a prefix code because this 1 1 is appearing here. So, this is the example, this example where this string could not be decoded uniquely because it could be broken into streams of code words in many different ways. So, it could not be decoded uniquely, and this code is uniquely decodable, but it is not a prefix code because this code word is appearing as a prefix of this code word, and this code is a prefix code. Okay. So, here is an exercise. Is this code uniquely decodable? So, when we try to answer this question, we have to see whether we can combine several code words which can be also broken into code words in a different way. So, if we try this way, then we will see that in fact there are such streams which can be broken into code words in different ways. For example, this one. If you take this stream can be, this bit stream can be broken into code words like this. 1 1 is a code word, then 1 0 1 0 is a code word, and then 1 1 1 is also a code word. Whereas this can also be broken into code words in this way: 1 1 1 and then 0 1 0 1 is here, and then 1 1 here. So, this stream can be broken into code words in two different ways. That means, two different symbol streams can be encoded into the same code stream. So, this code is not uniquely decodable. Okay. Now, we come to a very important source coding technique called Huffman code. So, we will see with an example first how to construct a Huffman code. So, if we have a random variable x taking 5 values, without loss of generality, we will assume that these 5 values are 1, 2, 3, 4 and 5. If they are named differently, you can put those names here. So, there are these 5 values this random variable can take, and we will write the design code words here, and these probabilities are known to us beforehand. 1 comes with probability 0.2, 2 comes with probability 0.15 and so on. So, the first step in designing Huffman code is to arrange these probabilities in probabilities and show the symbols in decreasing order. So, the symbols will be arranged in decreasing probability first. So, we have these probabilities. We will arrange these symbols in such a way that these probabilities are arranged in decreasing order here. So, these symbols are arranged in such a way that these probabilities are in decreasing order. Then we will combine these two probabilities, add these two probabilities to get 0.3, and then consider these two symbols as a single symbol. So, next step, in the next step we will combine these two symbols as 1 and write the probabilities again in decreasing order. So, the probability of the new symbol, which is the combination of these two, will be 0.3, and we already have these 3 probabilities. So, 0.3 and these 3 probabilities will be arranged in decreasing order here. So, the combination of these two symbols goes in the first location because it has the highest probability, and then the other probabilities. And while we combine two symbols, we will assign 0 to the first symbol and 1 to the second symbol. So, 0 and 1 will be the last bits of these two symbols. Later, we will add more and more bits on the left of these two bits. So, again we repeat this process Now, we will combine these two symbols into one and add their probability as the probability of the new symbol. So, what is the probability of the new symbol in this step? It is 0.45. So, 0.45, and we add 0 to this symbol and 1 to this symbol. So, 0 to this symbol, and this symbol came from 4. So, we add 0 here and 1 to this symbol. So, 0 and 1. Okay. Now, we repeat this process again. We combine these two symbols. So, we get the probability 0.55 here and add 0 to this symbol and 1 to this symbol. So, 0 goes to both these symbols. So, we have added 0 to both these symbols and 1 to this symbol, which came from here 1, and the last step we combine the last two symbols with probability 1. So, we are 0 to 0.55 and 0.55 came from these two, that is these two, and these two came from this one and the last two. So, we add 0 to this symbol and these two symbols, and we add 1 to this symbol. This probability came from these two, that is these two. So, we add 1 to these two symbols. So, this is the final code book we have, and this is the Huffman code. So, here we summarize the design process of Huffman codes. First, we arrange the symbols in decreasing order of their probability, and then we assign 0 and 1 as the last bit of the last two symbols, then combine the last two symbols as 1 and assign the sum of their probabilities to the new symbol. So, and then we repeat this process again and again. We again arrange these new probabilities in decreasing order and then keep doing this again and again. And while we when we want to assign a bit to a new symbol, that is a derived symbol, we actually add that bit to the left of all the symbols from which that new symbol came. We have seen that before. In fact, when we wanted to add 0 to this symbol, we actually added 0 on the left to all the symbols from which that new symbol came, that is this one and then the last two. We added 0 to all these symbols. Okay, here are some nice properties of Huffman code. Huffman code is a prefix code. Well, we are not going to prove it, but we can see at least from this example that this code is really a prefix code. There is no code word which is a prefix of another code word. For example, take 01. 01 is not a prefix of any other code word. 10 is not a prefix of any other code word. 11 is also not a prefix of any other code word. Okay. So, this is a prefix code. And then Huffman code is optimum, meaning by there is no code better than Huffman code for any random variable. So, if we have any discrete random variable, we cannot design a better code than Huffman code. So, that means Huffman code gives the minimum average length for any random variable. Okay. So, we will now conclude this class with few we will summarize what we did in this class. So, we have seen that there are two types of source coding. One is lossless, the other is lossy, and in the lossless source coding there is no loss of information. We have seen example, for example, we have seen the sampling at greater than Nyquist rate for low pass signals is actually lossless compression, and these are some file compression commands which use lossless source coding techniques. And then lossy source coding actually loses some information, for example, quantization, vector quantization and subband coding. and these lossy source coding techniques are used by these popular standards like JPEG and MPEG. And we have seen that instead of doing fixed length coding, that is instead of representing each symbol by a fixed length binary string, if we represent them with variable length code words after considering their corresponding probabilities, then we can represent a random variable with less average length than using fixed length code. So, while doing that, we have to keep in mind that all the frequent symbols like this with 0.5 probability should be represented by shorter sequences, and less probable symbols should be represented by longer sequences. So, that the average length code length will be minimum. So, we have seen that for this particular example of variable length coding, we have the average length 1.75, which is better than this. Then we have seen three types of three properties which are desirable in source codes, lossless source codes. This is not desirable, this is singular code where two code words may be same. In this particular example, all the code words are same. So, this code is not desirable at all, because you cannot decode the code at the destination. If you receive 0 here, we do not know which of these 4 was transmitted. So, a code should be non-singular, that is all the code words should be different. Okay, that is one desirable property. Another desirable property is it should be uniquely decodable, that it need not it should not only be non-singular, but it should also be uniquely decodable. That is, when we combine several symbols together, we get a long bit stream that cannot be decoded in two different ways. It can be decoded only in one way. So, that is uniquely decodable code. And then even uniquely decodable codes will not be decodable instantaneously. For example, if we receive 1 1, this symbol, we do not know whether we have received this symbol or we have received part of this symbol. So, we will not be able to decode this code instantaneously. So, for that we need another condition, that is prefix condition, that is no code word should be a prefix of another code word like this. Here this code word is a prefix of this code word. So, we cannot decode this code instantaneously. So, for that we need this kind of code where no code word is a prefix of another code word. Then we have seen a popular source coding technique, that is Huffman code, where we first arrange the symbols in decreasing order of their probability like this, and then we combine last two probabilities into one, that is here 0.3, and order the new probability with the rest in decreasing order like this. So, and while doing that, we assign 0 to this symbol and 1 to this symbol, and then we go on doing this again and again. And when you want to add 0 to this, we add 0 to this original symbol from which this probability came, and 1 to this. Okay. Then again we want to add 0 here, so we add 0 to these two and 1 to this one, again do that. So, we get this Huffman code, and we have seen that Huffman code is a prefix code. For example, this code is a prefix code, and Huffman code is also optimum, meaning by we cannot find any better code than Huffman code for any given random variable. So, this is the end of the summary, but we will do some exercise now on what we have done. So, this exercise says consider this random variable. This random variable takes these 7 values x 1 to x 7 with these probabilities. Find a binary Huffman code for this random variable x. Okay, so we will do as we did for the other example. So, we will first write these symbols here x1, x2, x3, we will write their code words here. Write these probabilities, they are already given in decreasing order 0.49, 0.26, 0.12, 0.04, 0.04, 0.03, 0.02. So, the first step in designing the Huffman code is to combine the last two symbols as 1. So, what probability do we get? We get 0.05, that will come before 0.04, but after 0.12. So, we again write the new probabilities in decreasing order 0.49, 0.26, 0.12, then we get 0.05, then 0.04, 0.04. We have got this new probability from these two. So, we assign 0 here and 1 here, that means we assign 0 to this symbol and 1 to this symbol, and these probabilities are written as they are. Next step is to combine these two symbols as 1 and we get the probability 0.08. So, we have got 0.08 from these two probabilities. So, we assign 0 and 1 here. So, 0 goes to this symbol and 1 goes to this symbol, and all the other probabilities remain as they are. Next step is to combine these two probabilities 0.08 and 0.05. So, we get 0.13. We assign 0 here and 1 here. So, 0 goes to 0.08, which came from these two probabilities, that is these two probabilities. So, we add 0 to both these symbols and 1 to this probability which came from these two. So, we add 1 to this and this. Okay. Then these probabilities remain as they are. So, then in the next step combine these two probabilities to get 0.25, 0.25, get 0.49, 0.26, 0.25, 0.1. So, 0 goes to these two probabilities. These two probabilities came from these 3, which came from all these 4. So, 0 goes to this and 1 goes to this symbol. Then we combine the last two probabilities to get 0.51. So, we get 0.51 and 0.49. This probability we have got from these two. So, we are 0 here and 1 here. 0 goes to 0.26 here and 1 goes to 0.25 to this one, and this probability came from all these probabilities. So, 1 will be added to all these symbols. Now, as the final step, we combine these two probabilities, we get 1. We add 0 here and we add 1 here. So, 1 goes to 0.51. 0.51 came from all these probabilities, all but the first one. So, we add 0 to all these symbols and 1 to 0.49, which is the probability of x 1. So, we add 1. Okay. So, this is the Huffman code for this random variable. Find the next question is find the expected code length for this encoding. What is the expected code length for this encoding? We have one code word of length 1 with probability 0.49. So, expected code length is expected code length is 0.49 times 1 plus 0.26 times code length 2 plus 0.12 times code length 3 plus 0.04 times code length of x 4 is 5 plus again 0.04 times code length 5 plus 0.03 times code length 5 plus 0.02 times code length 5, and when we multiply this and add all the terms, we get 2.02. So, this is the expected code length of this Huffman code for this random variable. And as Huffman code gives the best code for any random variable, we can also rest assured that 2.02 is the minimum expected code length we can ever get for this random variable. We cannot get any better than 2.02 expected code length. What is the minimum length of any fixed length code for this random variable? So, if we use a fixed length code, what will be the minimum length for this random variable? We have 7 possible values. So, to do fixed length encoding for this random variable, we will need at least 3 bits, because with 2 bits we can encode only 4 symbols, with 3 bits we can encode 8 symbols. So, here the number of symbols is 7. So, we have to have 3 bits to encode this. Okay. Next exercise, which of these codes cannot be Huffman codes for any probability assignment? Okay. So, to see why to solve this problem, we need to observe certain facts in the design process of Huffman code. So, what did we do when we tried to design Huffman code? We first ordered the probabilities in decreasing order and then combined the least 2 probabilities into one. So, and combine these 2 symbols as one new symbol from this step onwards. So, from this step onwards, these two symbols were considered a single symbol. So, the code, the symbols having the least probabilities, two symbols, last two symbols will have the same bits except the last two bits, that is for sure, because in this step we have added 0 and 1 to different bits to these two symbols. From then on, these two symbols are considered as one symbol. So, whatever bit is added from this step onwards to this probability was added to both these symbols. So, as you can see, except for the first two bits, the other bits of these two symbols are same. So, in other words, and also these two symbols will have the maximum code length, because they have the smallest probabilities. So, we can say that the maximum code length will be there for at least two symbols, and two such symbols will have these two code words differing only in the last bits. All the other bits of the longest two code words will be same except for the first last bits. Okay. So, after we have observed this fact, we can say that this particular code cannot be a Huffman code, because it has only one longest code word. So, in the design process, we have seen that the longest code word should be there for at least two symbols, and those two symbols will have the same code length differing only in the last bits. So, this cannot be a Huffman code. Can this be a Huffman code? Yes, this can be a Huffman code. We at least see that this satisfies the observation we have just made in the design process, that is, it has maximum length 2 and there are two code words of length 2 and they differ only in the last bit. So, this can be a Huffman code, and in fact, we can see that this will be a Huffman code for exactly this random variable. If we have a random variable taking values 1, 2 and 3 with probabilities 0.5, 0.25 and 0.25, then what will be the Huffman code? We will combine these two probabilities. So, first step is this, and then we will combine these two probabilities to get probability 1. So, we add 0 here and 1 here, 0 to this symbol and then 1 to both these symbols. So, in fact, we have got exactly the code that is given in the exercise. So, we have got this code, and this is a Huffman code for the random variable taking three values with probability 0.5, 0.25 and 0.25. So, this is a Huffman code for the random variable with these probabilities, and this is not a Huffman code because there cannot be a single longest code word in a Huffman code. The longest the maximum length should be there for two code words for any Huffman code. This can also not be a Huffman code because it has two symbols, and for any binary source the Huffman code will be just 0 and 1, because for a binary source, suppose the first probability is p and the other is 1 minus p. If the first probability is p, then the other must be 1 minus p, and suppose p is longest, the p is the larger, p is greater than 1 minus p, Then in the construction of Huffman code, it just involves one step. The total is 1, combine these two probabilities, we assign 0 here, 1 here. So, the code words will be 0 and 1. So, for any binary source, the Huffman code is just 0 and 1. It cannot be 0 1 1 0. So, Huffman code for any binary source is 0 1, it cannot be 0 1 1 0. Okay. So, in the next class we will do Craft inequality. Craft inequality gives a condition for existence of a prefix code for any set of lengths. So, if you are given a set of lengths say 2, 3, 4, 4, is there a prefix code of these lengths? So, the Craft inequality will answer that question. It will give a necessary and sufficient condition for existence of a prefix code for any given lengths. We will discuss about optimal code, we will see what is optimal code and what is the expected length of optimal code. So, this will also answer some questions about how much compression can be done for a random variable. And then we will discuss block-wise source coding. Here we will see that better compression can be achieved by coding many symbols together as a block. Instead of coding every symbol independently, we can combine many symbols together and do coding. So, that will give us better result. So, in this class we have covered introduction, uniquely decodable and prefix codes. Then we have seen what is Huffman code and how to construct that and some properties of Huffman codes. And in the next class we will do Craft inequality, optimal codes and block-wise source coding. And here are some reading materials from which these topics can be studied. Thomas and Cover Elements of Information Theory is a very classic book on information theory, and this is a more recent book by David McKay, Information Theory, Inference and Learning Algorithms, and this presents these techniques in a very lucid manner. So, I will encourage the audience to read this particular textbook. So, we conclude this lecture here. See you again later.